Hello friends, welcome to UGC EPG Pathshala. I am Swati Katya, Senior Research Fellow, Birla Institute of Scientific Research, Jaipur, going to discuss today about the accuracy assessment. Our episode includes the topics Introduction, Accuracy and Precision, sources of classification error, measurement of map accuracy, site and non-site specific accuracy, error metrics, indices of accuracy and Kappa coefficient. Let's start with the introduction. There is no classification created from the remote sensing data that can be completely accurate, as error originate from the different sources including the classification algorithm itself. In order to use the product of classification efficiently, the user needs to know how accurate these products are. This therefore necessitated accuracy assessment of the remote sensing classification process. In remote sensing, accuracy assessment is mandatory and is very important for providing information about the quality of the product of classification as well as furnishing the norms for comparing the performance of different classification methods. Accuracy assessment is an important step in the classification process. The goal is to quantitatively determine how effectively pixels were grouped into the correct feature classes in the area under investigation. Accuracy is defined as the correctness, that is, it measures the agreement between a standard assumed to be correct and an classified image of unknown quality. An accuracy assessment compares two sources of information. First, the pixel or polygon from the classification map developed from remote sensing data, and second is ground reference test information if the image classification corresponds closely with the standard. It is said to be accurate. In a statistical context, high accuracy means the bias is low. The accuracy of the spatial data that has been defined by the USGS in 1990 as the accuracy assessment or validation is an important step in the processing of remote sensing data. It determines the information value of the residing data to a user. Now we will start with the ground verification. Evaluation of classification result is an important process in the classification procedure. Traditionally, the accuracy is determined empirically by comparing with the corresponding reference or the ground data, wherein the results are tabulated in the form of a square matrix known as a confusion matrix. Ground truth data is a factual representation that has been observed or measured and can be analyzed objectively. It has not been secondary. If the data is based on an assumption, subject to opinion or up for discussion, then by definition that is not the ground truth data. If analytics are based on subjective data and assumption, analysis will very likely to be basic and therefore not valuable. Ideal situation is represented by diagonal matrix wherein only principal diagonal elements have non-zero, that is, all areas of the image have been correctly classified. Now what is precision? Precision is a measure of how close your experimental measures agree with each other. The closer each measurement is to the other measurement, the more precise the result will be. If the measurements are accurate value for a given target, the closer the values agree to each other, the more precise the result will be, which is clearly shown in the figure number 1. High precision means the variability of estimate is low. Now we will discuss about the various sources of classification error. In a manual interpretation, error are created by first, misidentification of parcels, second is excessive generalization, third is error during registration, and fourth is variation in detail of interpretation and other factors. A very simple landscape composed of a large uniform distinct categories is likely to be easier to classify accurately than one with a small heterogeneous indistinct particle arranged in a complex pattern, as it is shown in a figure number 2. Now we will discuss about the measurements of map accuracy. This is a task of comparing two sources of information, one based on analysis of remotely sensed data and another based on a different source of information assumed to be accurate. For comparing the information that varies temporally, the reference data should match with respect to time. To assess the accuracy of map, it is necessary that the map and reference data to be co-registered, that they both use the same classification system and minimum mapping unit, and that they have been classified at same comparable level of detail. For remotely sensed data to be truly useful and effective, an appropriate technique of accuracy assessment needs to be performed. Accuracy assessment can be defined as a comparison of a map produced from remotely sensed data with another map from the same source, as shown in the figure number 3. A determination is made of how closely the new map produced from the remotely sensed data matches the source map. Evaluation of the accuracy of classification of remotely sensed data can fall into one of two general categories. First is non-site specific assessment and second is site specific assessment. As it is shown in the block diagram of. Now we will start with the non-site specific accuracy. Non-site specific assessment is a simplistic approach of accessing the accuracy of the classification of remotely sensed data. In this method, a comparison is made between the known of estimated area and the area derived through the process of discrete classification remotely sensed data. For example, an estimate is made of how percentage of area represented by three categories. First is grassland, woodland and water. Suppose these known map areas are estimated to be 20% of grassland, 60% of forest and 20% of water. It is possible to compare the estimated area by a category to the classified imagery derived areas of each category. The area of each category derived from discrete classification of remotely sensed data consists of 18% of grassland, 61% of forest and 21% of water. After classification of the remotely sensed data, non-site error assessment of the derived map is done. Assuming that the area estimate of each of three categories are correct, the non-site specific error analysis would not indicate a significant problem with the classification of the remotely sensed data. Non-site specific error analysis consists of identifying general problems with resulting classification but provides no information about the locational accuracy of the assessment or how well each pixel was classified. Even though there was close agreement between the estimated area and the area derived from the classified map, the classification may still have been accurate in terms of locational or site-specific errors. If a substantial difference between the total area in the estimate and the total area in the classification occurred, it would be clear that the classification had not been well performed. Thus, the limitations of using non-site specific error assessment quickly reveal themselves. The proportion of three categories are similar in each map, but the physical location of each category in the resultant map is shown in the figure number 4a as well as in the figure number 4b, which does not match the original map. Now, after non-site specific accuracy, we will discuss about the site specific accuracy. It is based on the detailed assessment of agreement between the map and the reference data at a specific location. The goal of accuracy assessment is to estimate the accuracy of image classification using sample of reference data. Site-specific accuracy is based on detailed assessment between the two maps. In most cases, pixels are the unit of comparison between the classification error, that is the misidentification of pixels. There may also have been boundary error. Site-specific error analysis makes into account locational accuracy of the classification. This process makes a pixel by pixel comparison between the remotely sensed data derived thematic map and a true map of the area with the same theme. This accuracy assessment approach is still prone to errors attributed to control points, location error, boundary line error and the pixel misclassification. Usually, the purpose of classification is to derive the thematic map of some unknown characteristic of Earth's surface or some characteristic that has changed over the time. So, it would be unusual for a complete and current reference map to exist. However, the reference map can be represented by a sample of location within each theme of the area of interest. The selection, sample location and sample size is determined by the requirements of the subsequent analysis. In most cases, the analysis will include the interclass analysis as well as the overall accuracy analysis. Now, we will start with the data requirements that are required for sampling the data. The data requirement for performing a classification include remotely sensed data, ground truth training data for characterizing spectral parameters of each class, and an independent set of ground truth data. Since it is impractical to have a complete pixel by pixel ground truth map, an adequate subset or the sample number of points is needed for there to be a rigorous accuracy assessment of a classification. One must use an appropriate sampling technique that meets statistical requirement. Site-specific accuracy assessment can be evaluated for an overall classification on a pixel category basis. The more rigorous and useful approach is to evaluate mapping accuracy on a per category basis, which provides more insight into classification error that may has to be unique in specific categories. Category-specific errors are not readily apparent in an overall assessment. A stratified random sampling method is an appropriate sampling method for the accuracy assessment in a per category basis. The Kappa coefficient is an agreement which has a statistical measure of the significance of difference between the observed agreement of two classification versus the agreement due to random chance. Is commonly used in both type of assessment and requires a multinomial sampling method. A stratified random sample is a multinomial sampling method and therefore is an important sampling method to be used with the Kappa statistic. With the stratified random approach, points are stratified by a map category and a simple random sampling is employed within each stratum. Once the sampling design has been determined, the number of sample points must be determined. The number of reference pixels required for accuracy assessment depend on the minimum level of accuracy. Equations suitable for determining a minimum number of pixels required for different level of accuracy. Once the approach determining the total number of reference pixels to assess the accuracy at a minimum level uses the equation that is given below, which state the n is equals to the total number of points to be sampled, p is the expected percent accuracy, q dash is equals to the 100 minus the expected percent accuracy, and e states allowable accuracy. The equation which mentioned above states that and computes the ideal number of pixels to sample as therefore points for an overall accuracy assessment of a classification. As allowable error increases, the number of required sample point decreases. Assuming a stratified random sampling approach, the total number of reference point on a sample point required at a given expected accuracy and allowable error must be further stratified by a thematic category. When Gadrin states that a minimum sample of 20 is required for 85% of the accuracy, while 30 observations per class are required for 90% of the accuracy. When we calculate the above equation, an important point is locating random points. The simplest way to generate random point is to pick two random numbers, one of the horizontal and the other vertical coordinate. In the UTM coordinate system, one random number would be chosen for the casting and another random number would be chosen for the northing. This is simple to do in a GIS using grass. The program random can be used to identify random pixels in a raster map. Now we will discuss about what error matrix is. An error matrix can be useful when evaluating the effectiveness of a discrete classification of remotely sensed data. An error matrix is a means of reporting site-specific error. The error matrix is derived from a comparison of a reference map pixel to a classified map pixels and is originated as a two-dimensional matrix. This matrix takes the form of columns representing the reference data by category and rows representing the classification by category. An error matrix is also referred to as the confusion matrix or a contingency table, and in many cases the classification categories are arranged in the columns and reference data represented along the rows of the matrix. However, for consistency, the case of explanation, this document assumes an error matrix arranged according to the original definition shown in the table number 1. The standard form of reporting site-specific error is the error matrix, sometimes referred to as the confusion matrix. It defines not only overall error for each category but also misclassification between categories by category. It consists of a n cross n array where n represents the number of categories. The left hand side is labeled with the categories on the map. The upper edge is labeled with the same n categories from the reference data. The values for the matrix represent number of pixels for which the analyst has been able to compare the evaluate reference images. In the evaluation of classification error, a classification error matrix is typically formed. This matrix is sometimes called the confusion matrix or a contingency table. In this table, classification is given as rows and verification is given as columns for each sample point. The diagonal element in this matrix indicate the number of sample for which the classification results agree with the reference data of diagonal elements in each row present the number of sample that has been misclassified by the classifier. That is, the classifier is committing a label to those samples which actually belong to the other labels. The misclassification error is called a commission error. The off-diagonal elements in each column are those samples being omitted by a classifier. Therefore, the misclassification error is also called an omission error. For 5, pasture or hay were 7, coniferous forest was 0, deciduous forest was 0, open water was 0, were wrongly classified as a row crops. Across the row, we see what pixel mapped as a given category actually were when field verified. The diagonal from the upper left to the lower right gives the number of correctly classified pixels for each class. Row tables gives the total number of pixels to each class as recorded on the reference image column. Totals show the number of pixels assigned to each class on the thematic map. Misclassification can be identified by error of commission and error of omission. Error of omission inclusion is wrongly inclusion of a sample location in a particular category due to misclassification. Error of commission is off diagonal values across the rows. Error of omission is when the sample location is removed from the another category. Error of omission is the off diagonal values down the column. Now, measures of agreement. From the error matrix, several measures of classification accuracy can be calculated, including percentage of pixels correctly classified, error of omission and the error of commission. In addition, statistical measurements such as the Kappa coefficient of agreement, Kappa variance and a Kappa standard normal deviate can be calculated from the error matrix. The most commonly used measure of agreement is a percentage of pixels correctly classified. Simply the number of pixels correctly classified from the validation set of pixels divided by the total number of reference pixels. Percentage correct is calculated by dividing the sum of the diagonal entries of the error matrix by the total number of the reference pixels. Therefore, percent correct provides an overall accuracy assessment of the classification. However, if minimum classification accuracy is required, it is necessary to verify that the calculate percent correct for the overall classification does not indeed exceed the predetermined minimum classification accuracy with the same level of confidence. To assure that a minimum overall accuracy, a one-tail lower confidence limit at a specific level of confidence must exceed the minimum accuracy standard. For example, the lower confidence limit of a one-tail binomial distribution at a 95% confidence level can be calculated by the equation number 2 as given below, where the P states 95% confidence limit, P dash states the percentage correct for the category, Q dash is 100 minus the P dash, and N states the number of observation in a particular categories. As with the overall percentage correct calculation, if the confidence interval for a percentage correct of an individual category is greater than the minimum required accuracy for a site specific, then the accuracy classification of that individual category meets or exceeds the minimum accuracy for that category at a certain level of confidence. In addition to provide information necessary to calculate percentage correct for an overall classification or for individual category with the respective confidence interval, an error matrix also contains other information useful in assessing the accuracy of a classification. In addition, non-diagonal values in each column represent error of omission and non-diagonal values in each row represents the error of commission. There are 3 indices to evaluate the accuracy of attribute data. First is overall accuracy, that is also known as percentage correctly classified, where SD shows the sum of the values along the diagonal and shows the total number of sample location, and the equation is given below. Producer's accuracy. Producer accuracy is calculated in a similar fashion and user accuracy is calculated with only difference being that the total number of correctly classified pixels of category is divided by the total number of pixels in that category in the classification map. Instead of dividing the total number of pixels in that category in the reference map, that is the column marginal or a column total, probability of a sample spatial unit being correctly classified and is a measure of error of omission for particular category to which sample belong, where Ci shows the correctly classified sample location, Ct shows the total number of sample location in the column, and the equation is given below. Now we will discuss about the user's accuracy. User accuracy of reliability is actually the equivalent of a percentage error of an individual category and is calculated as a desired earlier probability that a spatial data unit classified on a map or image actually represent that a particular category on a ground. It is measure of error of commission, where Ri equates to correctly classified sample, Rt is the total number of sample location, and error of commission is given by 100 minus user accuracy. The omission error is given by 1 minus the producer accuracy and the error of commission is given by 1 minus the user accuracy. Now we will discuss about the Kappa coefficient. Kappa coefficient is a measure of a difference between the observed agreement between the two maps as reported by a diagonal entries in the error matrix. One of the advantages of using this method is that we can statistically compare two classification products for which the classification map can be made using different algorithms and we can use the same reference data to verify them. The equation given below states that table number 2 shows the calculation of the Kappa coefficient. The Kappa coefficient is a discrete multivariate measure that differs from the usual measures of overall accuracy assessment in basically two ways. First, the calculation takes up into account all of the elements of the error matrix, not just the diagonal of the matrix. This has the effect of taking into account chance agreement in a classification. Thus, resulting Kappa coefficient compensate for a chance agreement in the classification and providing a measure of how much better the classification well performed in a comparison to a probability of a random assigning of pixels to their correct categories. Estimated variance of the Kappa coefficient of agreement can also be calculated. This is the most useful in comparing two different approaches to same classification scheme by allowing a standard nominal deviate of a z-score to calculate. The z-score is used to determine if the differences in accuracy levels for two classification with the same resultant classification scheme are significant. The Kappa test statistics test that the null hypothesis that two independent classifiers do not agree on the rating or classification of the source. Now we will discuss about what are the uses of Kappa coefficient. Now we will discuss about what are the uses of using a Kappa coefficient. It compares two error matrices, it weights the cells in error matrices according to the severity of misclassification, and it provides error bounds on the accuracy. Hope you have enjoyed the lecture. Thank you.